Okay, so it is 6:02. Let me give a quick general introduction, and then I'll ask our program committee of the Corporate Liaison Program, Mary Baker, to introduce our today's speaker. Thank you very much for joining us. This is our 7th session of the Corporate Liaison Programs Industry Spotlight. And we usually have presentations from industry. This is hosted by Santa Clara Valley section of IEEE. Today, we decided to invite someone from academia. We don't want just to focus on industry because we too can learn from academia as well, and quite a bit for that matter. We will be recording this session. You can ask the question using either chat or Q&A at the bottom. I'll be monitoring both. The presentation will last for about 45, 50 minutes, and then we'll entertain questions. With that, Mary, would you like to introduce our speaker?
Yes, absolutely. So we are delighted to have Dr. Corey Baker here. He is an assistant professor in the Department of Computer Science at the University of Kentucky. And he is also the director of the Net Recon Lab, which focuses on cyber physical systems such as smart cities, smart homes, and mobile health. And the last time I got to see Corey in person was several years ago, before the time of COVID, at a conference where he and one of his wonderful students, Esther Max Onakoya, were presenting an earlier version of this work. And it was fascinating then, and now in the time of COVID, it seems even more relevant. So I'm absolutely delighted to be able to welcome Professor Corey Baker tonight as our IEEE Industry Spotlight speaker. Welcome, Corey.
Thank you, Mary. So thank you for the wonderful introduction. And as Mary mentioned, I'm going to talk to you today about some of the things of that has to do with remote patient monitoring and a lot of the work of my graduate students in particular. And so today's talk is Tolerable Delay, Augmenting Cloud Connectivity with Opportunistic Communication for Entity-Centered Apps. And in particular, I'll point that towards remote patient monitoring, and then also talk about some related applications that you all may be interested in as well. And so if you want to, I'll have these QR codes throughout the throughout their presentation. So feel free, if you have an iPhone, you can use your regular camera, or an Android if you have an application that can read QR codes. They'll take you to the link here. This will just take you to my research site, but I'll have some links to some of the GitHub repos that are related to the work that we'll be discussing here today. So what are some of the things we'll be talking about? One, I mentioned remote patient monitoring. What is that? What is the traditional sense of remote patient monitoring? And then what happens when delays are involved, and how can we use those delays to create communication in rural areas? And so many of you are probably familiar with delay tolerant networks. How can they be used in real world applications to kind of create connectivity there? And then I'll talk about how that can be crossed over later into what we like to call low-cost smart cities. So you hear nowadays every city wants to become a smart city. It's very expensive. What does those numbers look like? Why is it expensive? And then what you can do to create these low-cost smart cities with opportunistic communication. And interestingly enough, this word cloud here is about remote patient monitoring for medical fields, but if you look at a lot of the key words like confidentiality, cost, poor implementation, these things will kind of cross over with smart cities as well. And so these are some of the more interesting things that come up when people think about this space and things that need to be overcome. So remote patient monitoring. So I'll talk about this a little bit. We kind of are familiar with the general sense of how it works. So you may have a patient that's either at home or sometimes in the hospital still as well, and they have a number of sensors that may be connected to them. And remote patient monitoring is very useful because it allows you to not have to be in the hospital to have your symptoms monitored, and which of course can save a lot of money. But then also, if things happen at home, of course, doctors or others can react to them. And so sensors are connected to a patient. That many times that communication happens through a mobile device, and then of course, your mobile device is connected to the internet, and it could disseminate that information through the cloud to get it to the necessary medical entity. But many times there's issues with this part when it comes to connectivity. So how do you overcome the limitations of connectivity, particularly when it's limited or it's non-existent at all, right? And so you might think non-existent at all. Well, what does that mean? Well, 58% of rural settlers believe access to high-speed internet is a big problem in their area. And so there's been a lot of money trying to solve the problem of remote patient monitoring in rural areas. Particularly, there's been more than $22 billion spent, and we're talking about in the U.S. This is, of course, this makes sense for developing areas, but this money spent here is in rural areas. And when you think about many of the symptoms that are involved, many of these patients that can be monitored are in rural areas. And so how do you address a problem like this? Well, of course, I'm a computer scientist, and trying to solve this problem sounds cool from a technical standpoint, but attempting to solve it just in this space myself is almost impossible, especially trying to do it correctly. So one, there's so many things involved. Here, this is a team that I'm part of called Launch, which stands for Linking and Amplifying User-Centered Networks Through Connected Health. And a Launch consists of a number of different teams and entities. So one, in the middle, you see we have the lead cancer surgeon at the Markey Cancer Center here at UK, Dr. Timothy Mellett, along with to your left is two of my PhD students, one who Mary mentioned earlier, Esther, and then Allie, whose research I'll be talking about both of their research today, and some of the things that we're doing to overcome. But then, of course, you have the NIH, you have UC San Diego, that's part of the team, FCC. And so we come together as a team, different spaces, medical, non-medical, technical, as well as working with the patients and doctors to understand how can you deliver care correctly in these scenarios. And is the title of the talk says it's entity centered. So if you understand the entity correctly, in this case, patient, then hopefully you can design in a way to give the patient the information that they need within the tolerable delay. So what does symptom management look like, and why is it important for rural patients? So if you did not know, particularly in Appalachian Kentucky is the #1 place for lung cancer, and many other actual types of diseases as well. But particularly rural patient monitoring has helped all around the United States with decreasing the number of actual issues with symptoms in patients. But in rural areas, it's had little to no effect, mainly because of this connectivity issue. And so if you can provide treatment in a way and understand how to design applications to these particular patients, our hope is that we can provide better care and start translating what happens with remote patient monitoring to rural remote patient monitoring. So what does this look like in an opportunistic sense? To describe it, first I'll start off with a brief overview of delayed tolerant networks, just so I can put it in the right time or in the right set, so you can understand kind of how we're going to leverage delayed tolerant networks to deliver this communication. So as I showed earlier, I said there were sensors connected to a patient. When these sensors are connected to the patient, that information goes to their mobile device, and in a delay tolerant sense, and when I say delay tolerant, here this could be minutes, hours, days, as opposed to seconds. And so in this case, Alice and her mobile device may come in contact with another person here in node 1, and then eventually at some future time, say an hour or a couple hours later, they may come in contact with some other nodes, and then hopefully eventually come in contact with the doctor. Now here you might think, in a sense, this could take a long time, or it may never occur, and that's true. And so here of course, a delay tolerant network, if you compare that to a centralized network, something that's connected to the internet, you might say, well, why don't we just choose the internet way? But if you saw the numbers that I mentioned before on how much money it has been spent to create connectivity, over 22 billion, and think that 5G may solve the problem. You'll see that it's a very expensive problem to solve. So how can you provide this type of care now? So DTN can work maybe if you have enough mobility in the network, but as you can see, there's limitations with just depending on the DTN as well. So what about leveraging the opportunistic aspect of DTN to see how information will be transmitted when connectivity is intermittent, which happens in many times in these scenarios. Basically, you may have internet connectivity at some point and then you end up losing connectivity. So a couple entities I'll show in this figure. One is going to be, you'll see the lightning bolt that signifies internet connectivity, or you could think 5G. And then you'll see that when connected, the rest of the time I'll be talking about device-to-device connectivity. In this sense, you could think maybe Bluetooth or some other peer-to-peer Wi-Fi or peer-to-peer communication. And so when there's no connectivity, you'll see this red line. And then when there's connectivity in the second time frame, which you'll see in a second, it'll be blue. Or in the first time frame, it'll be blue. And then in the second one, it'll be gray. So to the left, thinking about the first image, in a similar case to our DTN scenario, the patient has some new sensor data to update that needs to go to the doctor. So their mobile device aggregates that information. And typically in the medical sense, particularly, I'm going to give a pointed example to lung cancer. The patients are typically older, not as mobile, and they are around their caregiver who typically is more mobile. So say they're in contact with their caregiver at the house, and then their caregiver within some time window. So you could think about this delay is say 30 minutes to an hour. The caregiver comes in contact with another device, but none of those devices have connectivity to the internet. So that's the photo on the left. So you'll see that the medical entity is far away. The medical entity itself has internet connectivity, and the doctor may or may not be at the hospital. But anybody that has the data that needs to be delivered in this current left window, this T0 less than equal to T1, currently does not have connectivity to deliver the information, right? And so you see the information has been propagated some, but not delivered. And what happens in the next sense, so you could think maybe 2 or 3 hours later, there's some mobility that occurs within a network where the caregiver is not around the original patient anymore or the intermediary node, but they've stored their information, and they can either deliver that to the medical entity, which has the internet connectivity, or you might have a scenario where the intermediary node came in contact with the doctor and they were to receive it. And so here, like I said, this could be minutes, hours, days. And in these scenarios, you might think, well, what if what about emergency information? So a lot of times when we talk about the medical case, many times people say, oh, well, if the patient's having a heart attack. And I want to point out that all types of medical information is not always emergency. And I'll talk about the types of data we're disseminating a little bit later, but everything is not necessarily a heart attack or something that needs to be responded to in real time. And so as long as you can understand the delays that's involved with that data, and as long as you can reduce that with this hybrid / opportunistic network, you can provide better remote patient monitoring than what was originally there. And so what are the entities involved? Remember, I said that a lot of this is entity centered and is the most important. Well, you've seen that there was a number of different entities in that figure that I just showed you. One, the patient. So the patient, of course, is the data aggregator. The data comes from them. Many times in the scenarios you're looking at, they may have limited mobility, and then they routinely visit the hospital. So in the case of what I'm going to show you a little bit details later, for the information that we're looking at, it's typically around 40 to 45 days that they end up going to the hospital. And when they're filling out this information on paper, the doctor's receiving this information usually within that 40 or 45 days. But there's things that occur within that window that if the doctors would have known about some of the symptoms that the patient's having, they could have provided better care. Right, so that routine visit you could think about as 45 days. And as the figure showed, they have intermittent connectivity, meaning that sometimes they have internet at home, sometimes they don't, or some of the patients don't have internet at home at all. And so then when you think about the caregiver and other types of local citizens that might be in the area, they're typically more mobile. The caregiver interacts more, of course, with the patient, so you can sometimes predict the connectivity that they may have of collecting patient information. And they move from points of interest, so they may go to the store, school, church, and those are typical places that they may move inside of in a rural area. In particular, we're talking about Appalachian Kentucky. And then, of course, there's a doctor hospital. At the hospitals themselves, the hospital that the types of hospitals we're looking at is usually a UK hospital, which from a location standpoint might be 2 to 3 hours away from the Appalachian rural area where some of the patients stay. And so there's some smaller hospitals along the way, and they typically have internet connectivity, but of course it's a hospital, so those places are stationary. And then there's points of interest where places like stores, Walmart, schools that may or may not have internet. And so you could think about in some of these scenarios, even though I didn't show it on the first figure, that depending on the delay that or how long the data has been out and needs to be delivered, you may try to route the information closer to a points of interest as opposed to trying to relate it or route it directly to the destination. So evaluating what happens when distress information, which is the type of information, I'm going to tell you what that looks like in a second. What happens when distress information of opportunistically transmitted from cancer patients to their health providers? So what happens when you disseminate this? So what does a rural area look like? Here is Owensville, Kentucky, and you kind of see some of the demographics. So one of the things that we do, if you're familiar with delay tolerant networks, has been around for over 20 years. And a lot of the work is set up in simulation. And then when you try to translate those, which you find in simulation to real world, you see that they don't operate as you expect them to operate. And so, or many times even the simulation environments don't reflect a real world environment. So from a simulation standpoint, one, we want to understand the demographics, the population, the mobility, and the density of these areas correctly. So here you see Owensville has about 11,443 people, 643 people. And then there's some information there about the density, gender, and then what are the age demographics of these people, and then to kind of give you some assumption about what the mobility in this area would look like. And so what we did afterwards is understanding the population is we came up with a transition matrix that's derived from the ATUS data. So this ATUS data could be found of many areas inside the U.S. Basically, it talks about how many people go to work, kind of what times they go to work. You can take this data and to basically find out or get a good evaluation or a good estimate of the mobility and density of the network. So here we basically took this ATUS data and basically created this transition matrix to get something similar to a real world understanding of how nodes would move in a network, and to understand how data, the distress information that I mentioned, will be disseminated in this city or in this county, Bath County. And so here's kind of the first simulation setup. So we did 100 different seeds, basically randomizing the simulation as much as possible. And we looked at how data would propagate over a 24-hour time span. So we looked at the adult population, which of course is going to be smaller than the original population, so 400, and then kind of just taking in the rest of the stuff that's in Owensville, and then try to have communication ranges that would look something like a device-to-device communication. So staying away from what more the theoretical thresholds, but more of what the real-world thresholds will look like. And so here you see kind of the numbers. We range from the number of patients, which are 2 to 10, and when you look at that compared to the whole population is not going to have lung cancer, but as I showed on the previous figures, the data generators are going to be those patients. So looking at real world or realistically in Owensville, there's about estimation of 10 people that are 10 patients out there that would have lung cancer. So ranging to see how much data they would have, and then of course pairing them with one caregiver as well, with having the one destination. So you see kind of the table there of trying to make this represent what Owensville would look like and its actual mobility. So what are some of the results that we've seen at first from the simulation? So when you look at latency, which is the graph on the left, what we did here is we varied the participating population. So many times if you looked at DTN research, you'll see that many assumptions occur where you assume that 100% of the nodes are participating. But you can imagine in this case, I've been talking about mobile devices disseminating information. Every node is not going to be willing to participate. And so how can you leverage or understand what happens when different nodes participate? So we have 3 groups of information that we're looking at. One, a full DTN. So basically there's no internet connectivity. That's the purple line. And then 2, we have the hybrid scenario, which is probably the more realistic scenario. When there's internet connectivity, you use the internet. When it's not, you disseminate opportunistically until you reach an internet connection or till you reach the destination. And then lastly, you have the fully cellular connected. And so as you imagine, when it comes to latency, the cellular in every case has the least amount of latency involved, right? And then when you have only 10% participation on the far left, DTN and the hybrid perform almost the same when it comes to the delivery latency. And as you start to increase participation in the population, you see that the latency for DTN and hybrid goes down. And then, of course, the hybrid is leveraging both the DTN and the cellular. And so from a latency standpoint, all of them keep decreasing. But if you get 100% participation, you have the lowest amount of latency. Now, I think what's interesting here is when you look at the delivery rates correlated with the latency, which I think is probably more important. So that's the graph on the right. When you look at the delivery rate, first looking at when there's 10% participation of the population, you see that the DTN and hybrid have about 40% delivery rate. And the cellular has less than 20. So you see that cellular, comparing it or correlating it with latency, had less latency, but it's delivering less data. And that's because I told you many of the patients are not going to have cellular connectivity. So when they do, if you do have cellular connectivity, of course, your data is going to be delivered quickly. But when there's not any connectivity, you're going to have a low delivery rate. And another interesting here is that you see once we get around the 30 to 40% participation, you start seeing that the delivery rate starts to plateau. And then as you increase, so we're almost able to deliver all the information that's generated by the patients, but then increasing population participation basically decreases the delay as you would expect. You're increasing the density in the area. And so since the density is increasing, you're having more movement, more people participating, you're going to decrease the delay. So another part is I told you that we varied the number of patients involved in here, which is essential to understanding how much data is actually being generated. It's going to have an impact on your delivery rate, and then of course your latency as well. So what you'll see on the left graph is similar, but in this case we varied the number of patients involved. So remember I told you 2 to 10. So the one on the left is when 2 patients are involved, and then you see that when it comes to delivery latency, when we increase to 10 patients, the latency of DTN and hybrid, it goes up some, but then remember you're having more data in there. So now when you look at the delivery rate, you see that cellular, even though you have more patients being involved, their delivery rate stays pretty low. The delivery rate stays pretty low, while the hybrid and DTN can continue to deliver information. But what's better here is you see that the hybrid scenarios is performing better than the DTN, which you would expect because it's able to leverage internet connectivity when available. So now going into so that's how data would be disseminated in these types of scenarios. But what about the entity itself, right? And so there's when we're thinking about the entity here, the patient, there's 5 million people over the age of 65. I mentioned and I showed some of the numbers for the lack of internet. And then there's also some assumptions here when it comes to understanding or familiarity with the technology itself. So I've been talking about cell phones. How is data presented to the user when it's but depending on the demographic and the area, are these applications designed in a way to where it best suits that particular entity, right? These things become important because, one, I said participation by the population and information from the patient, but if you present UIs and things to the patients that are designed in a way that encourages them to submit or add in wrong information, then you're going to get bad information on the end that's going to the doctor, right? And so it's very important to where you design systems, and I'll show you what a large system like this will look like, to have the patient involved and do what's called patient-centered design of understanding how they would like to see an application as opposed to, say, me wanting to design an application as a CS person. So I've been talking about the information. What does this medical information look like? So here, this is the NCCN distress thermometer. NCCN stands for National Comprehensive Cancer Network. And this distress thermometer is used in cancer centers around the country. So if you see a cancer center that has this NCCN designation, they're probably using some shape or form of this NCCN distress thermometer. And of course, I've been talking about lung cancer. For the Markey Cancer Center, they use this distress thermometer to measure distress, but this distress thermometer is used for many other comorbidities or other types of things that go on with patients. So it's kind of a universal thing. It's not just designed for lung cancer. Some of the ways that it's used here at UK is that the biggest thing is this meter that you see to the left. So a patient is asked to measure the distress level. And what happens is that it's been shown that when there's a recovering lung cancer patient, if you manage the distress, if they have higher stress levels, it's more than likely that they may have issues down the line, or their cancer treatment may worsen as opposed to get better. So measuring distress has been shown to be a good indicator of having patients recover from their lung cancer treatment. So the big one here is the distress, and some of the important things is that if a patient, say, hits a value of over 7, or if they hit a value of 7, 8 or above, then typically it's they're recommended to go to their doctor immediately. If they're around 5 to 5 or 6, sometimes they're referred to their social worker or some other entity to help reduce stress. And the other measurements below that, sometimes they're recommended some other things on to try to reduce stress. But it matters. The hospital is not the same everywhere. The numbers I gave you is kind of how the Markey Cancer Center tries to leverage the distress level of patients to trigger certain things of getting involved or responding to the patient. And then the problem list to the right is supplemental information that can be coupled with the distress level to kind of understand what might be triggering the stress of a patient. So this is the paper form. And so of course you may think that the first thing to translate is, if you want to use technology to translate this paper form to technology. And the reason why that's important is when a patient typically goes to the hospital, they might ask them to fill this out, but there's a number of other things that come about that are being researched, or sometimes the patient is not able to fill it out, or sometimes because of time, a nurse or somebody else may fill it out. And that has a different impact on what the real distress level of a patient is, because somebody may interpret somebody's stress level differently than what their actual stress level is. So one way is to try to translate this to technology. And there's a bunch of things involved that can be coupled together with, as you can imagine, there could be some sensor data that you may want to couple with this form that's currently not there, along with other understanding to try to bring together and understand the distress level, and then also reduce the amount of distress that the patient may have. So what we do is we have an application called Assuage, and we Assuage kind of the way we use is as you age. And so it's a symptom manager tracker, and it has 4 different user interfaces. And one, this is to do the wireless stuff that I was talking about earlier with the rural remote patient monitoring, but also to try to capture and try to understand how patients want to see data, and then try to design user interfaces in a way to get the most accurate data as possible, right? And so we also attempt to do a few different things with reducing the technical proficiencies of data and then closing the digital divide. So we have 4 different UIs per care plan. So here, a care plan, I mentioned the NCCN one, and then we have a launch one. So you see that there's 8, and these user interfaces that we can evaluate. I'll talk through it right now. So here, like I said, the most important thing is to collect accurate data. So first one is the original, which is most familiar to the patient, and that's that paper one that I showed you earlier. It's the easiest to use because it's the most familiar to them. And then, so what we did was take that paper one and translate it directly to an app. Assuage, the way we have it set up, is designed for iOS devices. So some of the design of this may look familiar. We're taking advantage of ResearchKit and CareKit on iOS devices. So you see how that the stress thermometer that you saw earlier, this is kind of what it looks like inside the Assuage app. So here, this is the straight translation of the paper. But there's also some limitations to doing it in this particular way. This requires the patient to have to navigate synchronously, meaning that they have to answer each question one by one, and in a sense, almost answer all questions because they're answering it asynchronously, or I'm sorry, synchronously. The next is the checklist format, which provides a little bit better navigation. It looks like the previous standard one, but they can skip through sets of questions. So if a patient is feeling stressed, they can just go directly to that section. And this is important because you can have data fatigue if you keep asking a patient the same information or questions they might not want to answer. They may either, 1, not answer the question at all, or 2, not answer it accurately. And I mentioned before, non-accurate information going to the doctor can lead to not the best diagnosis of what's going on with the patient. So here's the checklist format. Of course, I said they could do that asynchronously. And then the third one is the advanced one, which this one kind of looks like more of what you would see in a standard application nowadays. And so the patient can navigate synchronously or asynchronously. They can skip questions, go directly to them. They can answer on screen. They can swipe, tap. But this takes advantage of kind of all the UI stuff where these advanced UIs kind of make some assumptions that users are kind of familiar with certain things. So there's pros and cons, and it's not necessarily saying one is better than the other, but understanding how patients interpret many of these different things, because I talked about the age demographics and so on. And so quickly, I'll transition and talk about you've kind of seen the medical data, the way data can be disseminated, and then talk about briefly how this can be used to create what's called low-cost smart cities. So a low-cost smart city, 55% of currently living in urban areas, and this is projected to rise. And then there's increased demand on environmental resources. And many of you, and some of you might be in the space of, say, 5G. 5G is supposed to be increase connectivity and bring many devices online. But if you look at the data that's shown, more sensors are coming online and more data is being generated than 5G's bandwidth. And so not to say that what we're talking about is better than 5G, but it can be leveraged to facilitate some data that's not needed in real time. So if you can somehow create these low-cost smart city, understand the types of data that are being generated in them, and then understand what delays they can tolerate, you can basically leave a lot of that bandwidth open for data that's actually needed in real time and disseminate the data or delay tolerant data off of the main backbone. And so when you think about the money involved, smart city, the transformer smart city is very expensive. When you look at cities like San Diego, many of the places even outside of the US, it ranges between $30 million and $40 billion to become a smart city. So it's very expensive. And kind of some of the things that I'm talking about is saying any city can become a smart city. You just leverage what do you have around you, basically the mobility of people, vehicles, other entities, say bus routes, buses and bus routes, and you disseminate data with some type of delay. And so here you kind of see a bunch of different types of data that might be disseminated. Some of this is needed in real time, but then also you might look at this and say, oh, well, I would like to collect that data at some point, but it's not necessarily needed in real time. So here, when we talk about low-cost smart city, we talk about data that might not necessarily be needed in real time. So some of the research questions that we ask is, can we leverage pre-existing mobility of people in public transit to develop a DTN-based network architecture for low-cost smart cities, right? So can we leverage that hybrid, something similar to the hybrid architecture that I showed you earlier in the medical case for this low-cost smart city? There's some things that go on a little bit differently in a smart city case. I mentioned buses and bus routes. There is some predictability with some of the entities involved in a smart city. So leveraging that to get a good upper and lower bound on delivery and delay in those types of smart city scenarios. And then, so that's one of the research questions there. And then some of the future work is, can we improve access to care, the quality of patient care received when it comes to the medical case, and then basically help communities understand symptoms and how they can be monitored remotely. And then with that, I mentioned patient-centered design, but can we design better applications that, one, collects information from the patients better, but then two, create applications to encourage patients to get involved in the smart city way. And so another one is understand incentivization strategies, which I didn't talk about here. But incentivization, when you think about in the case of the smart city, you might have data sitting at one part of the city that hasn't been picked up in a while from a particular sensor or a couple of sensors. Well, if you understand how, say, people in the smart city or in the city take a bus, you may, the city may do something like, can I incentivize or discount this particular person's bus fare or their bus pass, their monthly bus pass, to encourage them to deviate from their path and say, hey, if you leave an hour earlier, if you take this bus route, we'll give you a discount on your bus pass. And really, you're asking that person to pick up data, right? And so what happens when you incentivize patients? One, what does it take to actually incentivize them correctly to do what you need them to do? And then two, what's the trade-off between this incentivization mechanism versus just paying for connectivity in general? And so now I want to kind of go into what some of the systems that we've designed look like and how they're involved in kind of some of the tools that we have available. So of course, when you're thinking about, I talked about connectivity and I talked about the data and this imaginary, well, at first I talked about imaginary application and I kind of showed you the different UI designs of a switch. But what does it take to create a system or technically a combination of systems that come together to kind of do this? So here I show a mobile device, which you can imagine is the user using a switch, and then we created a framework that connects to a switch which is using CareKit, which is called Parse CareKit. So this Parse CareKit, for those who are familiar with Apple's CareKit framework, it's open source and on GitHub. So they have CareKit itself, and then what we did is create a middleware and a backend that basically facilitates CareKit data called Parse CareKit to a Parse server, which many of you may be familiar with. Parse is an open source backend as a service, right? And so now you have data that can be synchronized between the mobile device, because CareKit data is typically local storage only. It's not synchronized to the cloud, and it's a developer responsibility to kind of get that data to the cloud and disseminating medical data or HIPAA compliant data, it's not the easiest thing to do. And if you do it many times, app developers may not be doing it correctly. So this is kind of a system that we designed to set it up. We have this middleware, which is open source. If you go to the QR code, you'll kind of see the link to the Parse Care Kit framework, but basically plugs into any Care Kit app and can pull the data from it. And then in our case, we sync it to our server, this netrecon.cs. And so netrecon, as you saw earlier, is my research lab, the network reconnaissance lab, but it connects to our server, and then our server is doing a number of different things. So it has a bunch of Docker containers, and here one of them is called Parse HIPAA. So this is this HIPAA compliant Docker container, which is running on three different servers, and this data is being load balanced. You all are, those are developing these large systems. Of course, you might have a system way larger than this, but here this is a fully HIPAA compliant system that's securely keeping the information encrypted at rest and in transit, and these can be thrown up and down at any point in time. So here we use Postgres 13 to kind of manage our data, and then our data, our whole system is set up with high availability using PG Pool 2. And so we developed this large system. But right, this is, in this case, you would think this is a fully connected system that when you have internet access, you can disseminate information. But in other cases where you have a situation where the internet connectivity might be limited, or even worse, not existent, right? In these rural areas, we also have this. Another tool called the SOS middleware, which SOS stands for the Secure Opportunistic Schemes middleware that facilitates the device-to-device communication, right? And so a bunch of things involved here to kind of complete and operate in this cycle. You have devices communicating with each other with this device-to-device, and then when internet's available, they send information to the cloud to essentially get that information to the doctor and vice versa. So I mentioned some of the things are open source. If you wanted to now, some of the tools you can check out online to kind of start building some of these applications yourself. These are the pieces of the whole system that I showed earlier that are open source. So one, if you decide to go to the link, there's a sample healthcare app. This app is built off CareKit, has some basic things that you can use with the framework, but then it also comes set up with the Parse CareKit cloud synchronization, right? And so that framework is already tied into the application, kind of shows you how to use it. And then what's also available is the Parse HIPAA Docker container that we have available. So there's a couple things that you would have to do on your own to encrypt data in transit, and then make sure that the data that's collecting is encrypted at rest and stored in the correct place. But other than that, it facilitates all the data, stores the data automatically. To test this out, all you have to do is, if you have Xcode, download the app, and then say download the Docker container, say Docker compose up, and you'll literally be running this on the local machine to kind of test out the tool and see how quickly these things can kind of get you up and involved. And then, as you know, if you use Postgres, PG Pool 2 and Postgres are both open source as well. So that's not designed by our lab, of course, but the things with the asterisk, the sample help app, and the Parse HIPAA and Parse CareKit are the tools that we kind of put out for the community to use and kind of build these types of health apps and medical systems. So finishing up, I want to just bring up one thing that I have set up that's called the Applied Machine Learning Intensive, or AMLE, and this is going to be for next summer. So I know this is an industry talk. You may know a number of undergrads or graduate students. This program that we have is to fund around 20 undergrad students for next summer, where a really competitive stipend. They get housing, everything included, room and board. And this program is sponsored by Google and NACME, which is the National Action Council for Minorities in Engineering. And so the program will support 20 underrepresented minority students. They'll earn upper division computer science credit. So if they're already students, they'll get this upper division credit. It's the intensive. It's very intensive. So it's 8 hours a day, 5 days a week for 8 weeks. So it's a very involved program. But during that time, the students will be picking up machine learning skills from the Google design curriculum to teach them machine learning that they can either apply, that they will be applying to research problems, but they can take with them a course that will benefit them towards industry. And like I mentioned, they'll get course credit. When it comes to, if you know other faculty members, or if you're thinking about getting involved, there'll be a submission of a 2-page proposal where basically they can, faculty can submit and say, I would like a group of students to work on a particular problem. So the first 5 weeks, the students are learning the skills that they need, and then the last 3 weeks they're applying it to a particular research problem. And then also, if you know current graduate students in the space of machine learning, looking for graduate instructors, the benefit here is that they'll get funding that will compete to what they can get paid in industry. But here they'll be teaching for 2 hours a day and then using the 6 hours, the other 6 hours to do research. So they can collaborate, them and their advisor can collaborate with my lab and my graduate students, and then they can also leverage that to get to work with the undergrads to, 1, teach them, but then 2, train them on how they can contribute to their particular research problems as well. And so is going to be a cool program. The first time that it's going to occur is going to be summer 2021. So feel free, this website, I just got the link, so it's not fully up yet. But feel free, if you know or have some interest, send me an email about it. And so with that, I'll take questions.
Hey, thank you very much, Corey. Great talk. So we have one question by Don Harris. It's a combination of question and observation.
Sure.
One of the cases is where the patient has very limited or no connectivity. Patients in rural, low-income situations would not have smartphones. The cost is typically amortized into the phone plan by the carrier, but these people do not have service. So any comment on this comment?
I would say, so the service is true. The assessments of, so if you recall, the team that I showed you before, that we're all working on this problem, is from a bunch of different areas. So the assessments that we've seen, a large number of the people, and I think I showed the percentages earlier, they have smartphone devices. The connectivity and paying for service is true. That part is often limited in rural areas in the United States. And so what we try to do is leverage the fact that people have mobile devices, and how can we use those mobile devices to disseminate information. There is in the areas a different understanding of how they leverage or use the mobile device, but the percentages of having the mobile devices themselves are there.
Okay, a couple more questions, and I have some as well at the end, but I'll give the audience opportunity to ask first. How big average data sets need to be synchronized? That's a question from Andrew Popov.
Wait, can you ask it again?
Yeah, no problem. How big average data sets need to be synchronized? I presume when you have disconnected devices, and then when they connect to the
Sure. I think that question might be coming from probably when I showed this slide with the data synchronizing from the device. And so if I understood, is how big or what is there a limitation?
How big are data sets?
Well, I guess, in these cases, this is not synchronizing a whole data set. This is the data that might be collected here when it comes to measuring when it comes to the app in Parse CareKit and CareKit, these the data is saved as outcomes, and these outcomes, they can be of different sizes. You decide how big they are. But if you recall, we're translating data that looks like this survey here. This data, when you translate this to a technical format, is very small, right? You have a bunch of binary questions, and then you have an integer measurement. So this data, translating this to an outcome, is extremely small. Now, I think it matters what other type of sensor data you want to look at. Of course, some of that it can get very large. And then when you think about disseminating it opportunistically, can cause an issue. But this data here is extremely small.
Okay. The next question from Zhensheng Zhang. How two nodes can communicate when they meet, using what protocol?
Sure, that's a great question because I hand waved over that completely. So one of the things that I mentioned is I called it a middleware, but it is the SOS middleware, which was designed by my research lab. That lab leverages Bluetooth communication, peer-to-peer Wi-Fi to disseminate information. So it does a discovery automatically when devices come in contact, and that middleware is running under the mobile applications. And so it makes a decision, all right, I'm in range, we can connect, and then it disseminates the information device to device. And of course, the parse care kit framework handles what I mentioned before, disseminating the information when cloud connectivity is there. And so we look at the apps that I showed you are using either Bluetooth or peer-to-peer Wi-Fi.
Okay. I think there's a variation of this question, which is also related to a picture. How can cloud help to reduce connectivity problem in remote patient monitoring case?
How can the cloud?
Yeah.
Well, the cloud. So if the cloud's existent, if it's there completely with no intermittent connectivity, the cloud is perfect. What happens is that I think I showed very early. It's going to take me a second to go back through the slides. That remote patient monitoring has helped everywhere in the U.S., and that's assuming remote patient monitoring with cloud connectivity has helped everywhere in the U.S. in reducing issues with patients and providing better care, except in rural areas, and that's because connectivity is not there. So in those cases, the cloud essentially is not available to the patients, so it's not able to benefit them. So of course, the cloud would be wonderful, but when you look at, I think I showed a number of $23 billion being spent already, and there's still not connectivity in these rural areas in the U.S. So those are actual numbers in the United States.
Okay. And I think what you just said is probably the answer to the following question. Why the delay in the cellular case in hours in some of the simulation results?
Oh, that's a really good question. So remember, this is based off of I'll use this one. This is based off of the Bath County, when I showed you the graph. In these areas, this is based off the realistic, there's not cellular data everywhere in that area. So if you're thinking about, a place, say, if you're thinking about San Jose, right, where I did my undergrad in San Jose. And so if you're thinking about there, you have full connectivity everywhere. And so you would say, all right, the delay should be milliseconds. I don't know, worst case, maybe a minute. But in these cases, internet is not available. So here you're depending on when either the patient themselves had internet connectivity or they get internet connectivity based off their actual mobility, or two, if their caregiver has the data, if they come in contact with cellular connectivity in the Bath County area. So that's why you kind of see the longer delays there.
Okay. The next question, is the paper focused on data collection? Is there any development of machine learning to detect issues on a patient? That was by Gabriel Orozco.
Of course, there's a number. I think there's a number of research out there on machine learning to approach the problem, or even trying to address issues with understanding the data. None of the things that I showed use machine learning to do anything with disseminating information or understanding the patient data. So here, what we're trying to do is the data collects the information from the patient, it gets disseminated, and then once it receives the doctor and their team interpret the data themselves. There's not any machine learning interpretation, but of course, that could definitely give you some insight in understanding what's going on with the patient.
Okay, and the last question I have here, and then I have a bunch of questions, but they're very quick. What simulator have you used to evaluate performances?
So here, because of what we're looking at, so the links, I think I put the paper names at the bottom of some of these. If you look at that same GitHub page, the GitHub repos and the simulation tools that we created to evaluate this is available on GitHub for you to use right now. So most of the work here I showed has just been recently published, and we created the simulation tools for this in Python. Depending on what we look at, and many times we use what's called the opportunistic network emulator, and then of course there's other things like NS3 that can be used because of what we're trying to look at in particular with understanding the ATUS data and basically how data can be disseminated. We didn't need to use a fully involved simulation tool like or NS3. And so here, this was based off the Python simulation tool that my grad students created. But like I said, it was designed for these particular types of scenarios, and is not intended to replace something like the one simulator or NS3, because those are very intensive simulators.
Okay, thank you. I got another question from Zhang Zhang. Machine learning is used for increasing connectivity or selected data to be transmitted, or other areas?
It could be used. I guess it could be used for any of those areas. I didn't talk about machine learning used on any of the connectivity pieces.
So let me dump on you 4 quick questions, if I may. First, have you considered satellite communication as a means for rural areas? There's a lot of development recently.
Sure, that's a great question. So when I mentioned launch, there's some of the partners that are with us are introducing satellite communication to see how it can be used. Even with some of the teams are looking at the connectivity, the area that I look. So with the launch, I guess I might have misled with launch. The case is for us to provide the best patient care period for the patient. Where my part comes in, and my team's part is doing the opportunistic communication that you've seen. So we have providers with this that are looking at providing the satellite communication that you mentioned, also trying to encourage current cellular providers to give connectivity there as well at different rates. So there's a number of different ways on creating connectivity there. The part that my research looks at is how can you leverage the opportunistic case?
Okay. 2 other use cases that I thought might be of interest to you based to your preferences. One is campuses, because they are pretty constrained, so you have limited scale, although you can scale to the higher degrees and have similar issues with security. So it's up to you whether you want to consider that. And then the second one is military, because they have these some aspects like stress level, and things like that. So they may have so these are just comments. And then the last question is, I think when Mary and I started our careers 20, 30 years ago, or, plus minus, there was a lot of research in ad hoc networks. So I'm just curious, have you found any applicability of the results from, these ancient times to your current work?
Yeah. So with your so you're right. So your point about Monets and mobile ad hoc networks is very relevant to the case. DTNs, of course, is a subset of mobile ad hoc networks, and both of those have been investigated for a while. I think some of the limitations that we've seen is when these types of networks have been translated over to real world, what are the limitations, right? And so one of the things that I guess when I was in graduate school and going to the cases of when you mentioned campus or in traditional social networks, creating the initial design or developments for the SOS middleware that I developed, and that was used to do real world measurements and real world DTNs, right? So it's meant to go away from just looking at simulations to how can you evaluate any routing protocol in a real world situation. And then as you mentioned, going in scenarios that are not just medical. I just talked about the medical case here in a low-cost smart city, but the first places that I started out was looking at creating these delay-tolerant social networks, right? So when you have a natural disaster happen, how can people leverage communication, basically what I call like a poor man's Twitter, and disseminate information when connectivity is not there? And so mobile ad hoc networks are useful. What happens is that you typically have issues when your network starts to fragment. And so what I say is that, or my belief is when you're using a delay tolerant network, if you can get it to work, it can leverage many of the benefits of M&A, but then it could stand in the way and work when the network fragments.
Okay, great. I presume Mary may have some questions. She's here.
So I was wondering about the applicability of this work to tracking COVID or other potential pandemics, or maybe even tracking vaccination programs. I don't know if anything needs to change, if there are any challenges for those kinds of scenarios here that are different than the ones you've handled so far.
Sure. So of course, I'm by no means a COVID expert, but I think your point is so here I show 2 different care plans and then show 4 different UIs for each of those care plans. So in the situation like you mentioned, there could be a COVID measurement care plan where you're trying to understand what's important to COVID, and I haven't looked into that at all, so I'm not going to attempt to even speak to it. But you can imagine that there's, say, a systematic way of how you want to evaluate COVID, and the way that Assuage is set up, because this is a medical research application that's meant to be able to assess anything. And right now, we're just currently looking at lung cancer. We will be able to put that information in Assuage and then understand UI capability and limitations, as well as disseminate information opportunistically.
Cool, thank you.
Okay, I think this exhausts all the questions. Thank you very much, Corey. Extremely interesting, insightful, and useful of all presentation. We highly appreciate you spending the time, especially those busy times when you just completed your grading and everything. So thanks. And also thanks to the audience for sticking with us at these late hours at different parts of the world. And Mary, thank you for introduction.
Oh, my pleasure. Thank you so much, Corey, for this fascinating presentation. Thanks.
Yep, thanks for having me.
Okay, bye everyone.